Now let's continue with the meshing. We have already obtained the fluid domain of the pipe segment as shown previously. It was done in design modeler. Now go to mesh and double click it. It may take some time to open the mesh. Here we have our fluid domain. Now before meshing we should give some named selections to different locations so that our solver will later know that which part is inlet, which part is outlet, and which part is the wall. So let's keep the named selections. So let's select our inlet. Let's select the surface, right click and create named selection. Let's name it inlet. Okay. Likewise, let's name this surface outlet. Select the surface, right click, create named selection and outlet. Okay. We can see the named selections here. We have created inlet in this surface and outlet in this surface. Also, let's make a named selection called wall. These outer surfaces will be called wall so that the solver will know the boundary inside which the fluid will flow. Now let's hide the inlet and outlet surfaces so that we can select the wall surface. So left click inlet, press Ctrl. Pressing the Ctrl key, let's select the outlet and right click, go to hide faces. Now these faces are hidden. You can see it here. Then instead of selecting these wall surfaces individually, we can go to mode. We can go for box select and we can just drag it and select all the surfaces. These surfaces will be named wall. So go to named selections, right click, insert named selection, and we have already selected these 5 faces here and rename it to wall. Okay, now we have all the named selections here. So let's unhide this inlet and outlet. Uh, so hidden faces, and this is the wall, outlet, and inlet. Now let's go to meshing. Uh, so click on mesh, and now we'll have to change some parameters here. We will have to check different parameters here, like for what purpose are we doing the mesh under this physics preference. Let's select CFD. As we are doing the meshing for our CFD, let's now choose the solver in the solver preference. Let's go to CFX as I find its interface quite simpler in comparison to Fluent. And now let's select the element size. Go for the appropriate size of element. The unit is in meters, so let's go for 0.005 meter, which is 5 mm. You may also go to even finer meshes looking at the graphics and processor you have in your computer. So at the beginning, it's just hit and trial. You just give the minimum element size and check for the mesh. Here I have given the mesh size 5 mm. So let's go to mesh, right click and generate mesh. Now it may take some time to generate. We can view the update in mesh. Looking at the bottom, you can click it and see the update. It is consuming a little more time, so let's stop this mesh and let's change the element size to 10 mm, 0.01 meter. Let's again generate the mesh. Okay, now the mesh has been generated and you can see it here. The mesh size is 10 mm. Looking at the mesh, we can see it distributed in a good way. We can see the mesh are mostly quadrilateral. We can also prefer the shape of the mesh. We can make it either quadrilateral like shown here, or we can also make it triangular. For that, let's go to mesh, right click, insert method, and just select the geometry body. Okay, the geometry is selected, apply. Under the method here, we have automatic. We can select it to be tetrahedrons, or we can also make it hex dominant. Uh, with the quad shapes of mesh we have here, we can make it hexagonal mesh. We said hexagonal mesh. Mostly the industries prefer the hexagonal mesh as they are quite uniformly distributed and the flow can be more accurately seen in the result. If we want to go for tetrahedrons, select tetrahedrons, and remaining let's leave it the way it is and go for mesh and generate it again. Okay, now here we can see the shapes of the mesh. We can see triangular meshes. Triangular in surface give tetrahedral mesh, and if we have quadrilateral shaped mesh while we see the surface, then it is hexahedral mesh. Okay, now let's again make this mesh to x dominant. Let's go to pass conforming method, and under this method, now let's choose x dominant and generate the mesh. Now we will have x dominant, meaning that the maximum number of meshes we will obtain will be in hexahedral shape and some might be in tetrahedral shape. Now the meshes are seen in quadrilateral shape again. This is hexahedral mesh if observed in 3 dimensions. We also have other parameters of sizing, quality, inflation, and other advanced functions here. So under sizing, we have adaptive sizing. If we on the adaptive sizing, then the meshes will adapt as per the element size we have given here. The adaptation will be done by Ansys itself. And if we turn off the self-adapting, then we can also go for capturing the curvature. If we turn the capture curvature to yes, then it will capture the curvatures and it will make the size of meshes more fine at the curvatures. Let's go to mesh again. Let's mesh it again. Okay, now here we can see these curvatures. At the curvatures, the mesh size is quite refined. We also have some other features here. Let's leave them as they are. These are some advanced functions. Okay, now here we can see the number of nodes and number of elements. Here we have around 1.1 million elements. If you are using the student version of Ansys, then I think the student version will support about 100,000 elements. But in this regular version, we don't have that limit. We have done the simple meshing in mesh itself. But for the industrial works for CFD, this ICM CFD is preferred as this ICM CFD provides us with high quality meshes, more uniformly distributed and which will be more suitable for obtaining results with high accuracy. But for now, let's carry on with our own mesh for our simple project. Now the next thing we will do is the input of boundary conditions. We will carry on with the setup in our next video.